line. So I know how to draw the tangent line actually. The question is how to draw the tangent vector. How to find the tangent vector on a curve at a point actually. Self-derivative. The tangent vector is a unit vector. You need to also divide it by the magnitude. Okay. So the tangent vector at any point t on a curve is that take that curve at that point, compute its speed and divide it with its magnitude. Okay? Divide with its magnitude.
So unit vector ये कैसे आया था? Magnitude से क्यों divide करें?
क्या मतलब?
इसको unit vector
we say that all these vector, tangent and normal and binormal vector, you treat them as unit vector. Okay? I mean, even if you don't treat them unit vector, it's fine. They're gonna have some magnitude, but we're gonna keep that magnitude 1. I mean, imagine that you have these vectors which doesn't have magnitude 1. You can normalize them to have a unit vector in their direction actually. Okay, so instead of taking the vectors that are not unit, it's better to take those vectors which are unit vectors because we know their calculation will be easy, that their magnitude is 1 actually. Okay.
Sir.
You can take.
So tangent vector this shows 8 point t, or we will take the entire curve p of t.
What do you mean? Sorry, yes.
Because this will give us at just one
tangent
point.
On the point p of t on a curve is going to be that, okay, you compute the derivative of the prime of t at that time and divide by the magnitude. Okay? One exercise. This tangent vector depends on a parameterization. Prove that this tangent vector is well defined. So p of t is well defined. In other words, it's independent of the choice of parameterization. Tangent vector wouldn't change. That would be same actually. So you're going to have one and the unique tangent vector no matter what parameterization you have actually. Okay? Now I'm interested in what? I'm interested in computing the flux of the F. You have to keep one thing in head, and that's very important. This flux is, so like this flow is not like this F does not only exist on this curve actually, but I am only interested in that part of the vector field that is associated with this curve actually. I'm not interested in the entire vector field, how it is moving in this entire region, or how it's flowing and behaving in the entire vector field. I'm saying that how it is behaving on this curve actually. Okay, so how much part of this vector field is kind of having a kind of a flux over this vector field on this curve. Okay, so here's the thing. So I need to do what? Take your vector field at a point on a curve. So you need to evaluate at the point p of t. So that's a vector field at a point, an arbitrary point on the curve. Okay? And I would like to do what? I would like to take the dot product of it with what? The tangent vector at the same point. And so when I'm taking dot product, basically I'm saying that how much of f is going in the direction of the t actually. Okay? And you want to do this on the entire curve. By the way, what is the nature of this quantity?
Scalar.
It's just a scalar. It's a scalar field.
It's a scalar field.
It's a scalar field because for every t you have a scalar association. Okay, it's a scalar field. And I know how to integrate the scalar fields. Okay? I know how to integrate the scalar fields over the curve. See, so this integral of this scalar field, which is the dot product of f with the tangent, in other words, how much of f is going in the direction of the tangent vector, and you would like to basically have this entire, you would like to have this on entire curve C actually. You're going to call this, or I'm going to give it a name, that this is the flux of the vector field C over the entire curve C. So that's my definition for the flux of the vector field on the entire curve C. So what you have to do, if you have to compute the flux of a vector field on a curve C, take this, vector field, scalar field, and integrate it over the entire curve. Okay, and we know the intuition for this scalar field as well actually. And I know how to turn. I know that if you want to compute the integral of a scalar field, you can turn it into the Riemann integral. So you can directly compute it. J.
अगर हमारे जो ये जो टेंजेंशियल वेक्टर है अगर ये यूनिट वेक्टर ना लेते तो शायद ये चेंज नहीं है अलग से होना
number would change, but as I said that you can say that okay, you can draw vector that are parallel to the tangent over what do you call this onto the entire curve. But one thing is that there is no point of changing the magnitude of it actually. Okay. So what we are saying is that why I am representing a vector with 2i plus 3j, why I am not putting any other vector, unit vector. Even if there is basically instead of a, you put any other vector, say 2a plus 3b, okay. But I know that each of this vector can be written in the terms of I and j, and eventually you can break down everything in the terms of the I and j unit vectors actually. Okay. So even if a vector, you choose, this tangent vector not to be a unit vector, okay, still you're going to have, what do you call, the same kind of a result, but this unit vector is going to do what is going to make your life, is going to make your calculation very simple. That's what it is. It's just convenience, it's nothing else. Okay? Is it making sense? Another exercise would be prove that this is independent of, so this map is well defined. So this guy is well defined. Okay. Now let me do one example for example computation of treat this as a definition actually. Obviously, in this definition, I'm going to assume that f is not just vector field, but f is continuous actually. Okay, so it's a continuous vector field. So let's do one example. For example, computing the scalar field. So here's and one example for computation of integral of a vector field over curve. Okay. So here's one example. So imagine you have curve this. So you have this catenary y equal to cos hyperbolic x. Okay. And you are treating this curve entirely. Not between, you're not taking it infinitely, you're just taking it from between 2 points actually. It's a curved segment between 0, 1 and 1 and cos hyperbolic 1. 0, 1 and cos hyperbolic 1. Okay. So that's my curve. So this is the description of the C. Now it's a cleverly written curve. It's written in rectangular form, but I know if you have been given rectangular form, you can write its parametric form very easily. It's not a difficult thing. And the field that we need to integrate, okay, the field that we need to integrate is x plus y. So that's what I have to integrate actually. So imagine I have a field that, as definition x plus y, and I would like to integrate it. Okay. Now, if you get back to the definition of integrating the scalar field on a curve, so what you need to do? You need some limits, which we apparently don't have here, but we have something else, from which we can deduce what should be the limit. Okay, and you need some parameterization. Okay, P of t that you need to substitute into the vector field f, and you need to compute the derivative of the parameterization and integrate with respect to the t. Okay, that's what you will like to do. That's what I would like to do. Question: how to find the parameterization? So what is a curve? Okay, that what would be the parameterization for this curve? So how can I find it?
So shall e power t plus minus e power minus t.
I don't have to think too much.
Or t.
So if you have a function, say a general function y equal to f of x, and you would like to write it as a parametric form, so what are you going to say? Let's assume that x is t. Okay, then for this corresponding t, what would be y? So it's going to be cos hyperbolic t. So that's the parameterization of this curve. Okay, and I'm saying that I want this curve, but from this point to this point. Okay, the question: for what value of the t, this will turn out to be this number, and this will turn out to be this number. So in other words, what is the range for the t actually? So it's 0 to 1.
0 1 include होगा?
क्या मतलब?
Open interval.
Yes, between. So it would be included actually.
Integration में बने.
ठीक, it would be included. वाले कर्व में तो फर्क नहीं पड़ता. Area wouldn't substantially change because of these two numbers, but yes, they are included actually. ठीक है, you have it. So you got parameterization. Okay. Now, what is your vector field? F. So F depends. So this is like your x of t. So this is like your x. Okay, and this is like your y actually. So that's your y of t. And what is your scalar field? So in other words, what would be f of p of t? In other words, what would be your x of t and y of t? So what definition is given to me? That it's x plus 1. So in other words, this is x of t plus y of t. And I also know the value of the x of t purely in the terms of the t. So this would be t plus cos hyperbolic t. Okay. So if the parameterization is given to you, all this stuff is very easy, not a difficult thing. Okay? So what I would like to do next? So I have f of p of t, so I need p prime of t. So what would be the p prime of t? And its magnitude. So this would be the magnitude of 1 and sine hyperbolic t, and this magnitude is going to be square root of 1 plus sine square hyperbolic t, okay? 1 plus sine hyperbolic t and its square. Okay, so this will be the magnitude of it. Huh? So it's 1 plus, yes. So this will be equal to cos hyperbolic t. ठीक है? Cos hyperbolic square minus sine hyperbolic. This is fine. This is true. So cos square minus sine square is 1. ठीक है? You have it? So what I would like to do now? So everything is right in front of me. So it's now, it's peanuts to compute this integral f over this entire c. So it's going to be, you take 0 to 1, f of p of t is t plus cos hyperbolic t multiplied by cos hyperbolic t and dt, and you know how to compute it. Okay? So if you have been given the parameterization, you have to just see that what is the definition of that. Now, this was a clever bit because it, we have to make sense of it that this is the scalar field that you're talking about. Okay. What would be the integral of say vector field?
सर हमारे जो स्केलर्स होते हैं सर वो भी वन डायमेंशनल वेक्टर हम बोलते हैं सर
Scalars with them क्या होता है?
सर जो स्केलर नंबर होते हैं
They are yes.
वेक्टर सर स्केलर उनको वन डायमेंशनल वेक्टर भी बोलते हैं तो सर हमारा जो ये सारा वेक्टर फील्ड का है सर तो इस जगह हम अज्यूम कर लें कि हमारा जो वेक्टर है यहाँ पे वो वन डायमेंशनल है तो जो
So it would be Riemann integral. जो पहले पढ़ के आए हैं, that would be the particular case of this actually.
तो सर हम जो पहले सारा काम करके आए तो इस पे ऊपर काम करें तो स्पेशल केस बना के फिर सारा उसके ऊपर करें।
I mean, in the sense that वो पिछली integration, the theory of integration that you have learned previously in your, you can see that is a particular case of it actually. ये उसकी generalization है. ठीक है जी. So let's. So here's an example for the computation of vector field. So in other words, I would like to compute that what would be the integral of a vector field on a curve. So what do you need? So for curve you need parameterization, and for f you need its definition. That's it. That's what essentially the two things that you need. So imagine C that is given to me, the curve that is given to me is a semicircle actually. Okay, so it's P of t, t square root of 1 minus t square, where the t sits between minus 1 and 1. Okay, that's the curve that is running. I need to integrate over this curve, but a vector field. And the vector field is defined as a two-dimensional vector field. So f of x, y is say x square and z. Okay. So whenever you have been given P of t, for example, in 2 dimension and 3 dimension, like you have to by default, whenever you have to by default understand that this is my x of t. And the second component is y of t. So if you like to compute what is f of P of t, you are asking what is f of x of t and y of t. So I know what is my f of x of t, so it's x of t, so it's going to be t squared over there, so this will be. We need to compute then t of P of t, the tangent vector at the point P of t. Okay, so I know that I can compute it by computing the derivative and computing the integral over it actually. So this is going to be. So what would be the P prime of t? So it's going to be 1 and minus t over square root of 1 minus t square. And everything is divided by P prime of t, so it's going to be, divided by, okay, it's like multiplied by the scalar. So it's going to be square root of 1 plus t square over 1 minus t square. Okay? So this finally is going to be, we could have played cleverly, because whatever this quantity is, I'm not interested in it, think about it, because when I'm going to take the dot product of f with P of t, this second component would be multiplied with 0, so it will go away actually, so I don't need to calculate it actually. I mean, if you usually calculate it, there's no need of it. So what would be f of P of t dot product with P of t, so it's going to be, so first of all, this would be 1 minus t square plus t square, so t square get cancelled, so this is just 1. So you are taking this vector multiplying with t square 0, so this is t square. Just think about it. What do you need here? So you need this. So you computed this now. And I would like to compute, the integral of this scalar field. So what would be the integral of this scalar field? Now let's get to the thing. So what you need to do, so I need to compute f dot t, but what is meaning of f dot t? That okay, you take f of p of t, then you take p of t. In other words, take your scalar field and multiply it with the magnitude of t prime of t, then integrate it with respect to dt over the entire domain, whatever you have. So what domain we have? So you have -1 to 1 actually. Okay.
So you multiply here, no,
They can interpret it. That's a scalar field. Okay. So this is like my f, and I would like to integrate this f. So what I'm going to do? I'm going to substitute p of t in my f and multiply with the magnitude of t prime of t. As per definition. So this is going to come. Okay? So you know this value that this is t square. You know this value that this guy is 1. And you are integrating t square over -1 to 1. You know how to integrate. Okay? See that this will turn out to be 2 over 3 to t. 2 over 3.
सर ये p प्राइम का
हाँ भाई.
ये जो p प्राइम ऑफ t का मैग्नीट्यूड है उससे
Start.
मल्टीप्लाई
This is a scalar field. I'm giving this quantity name f, compare it with f. So you are integrating an f over phi. So what do you need to do? Substitute your path into the f and multiply by the norm of p prime of t, and that's what you are doing. That's what you are doing. Okay?
यस
So you know how and what and why the definition of vector field and a scalar field along a curve, line integral of a vector field and a scalar field along the curve is actually, okay? And it makes sense that it should be the way it is. You can't get any other way. There are some of other things as well. Imagine I would like to integrate a very special kind of a vector field. So I have this. I would like to integrate a scalar field that is 1. Question. Tell me what would be this. By the way, I would like to say another thing. ये जितनी भी definitions है, all these definitions, and wherever I'm going to use curve till the end of the course, I'm going to mean a rectifiable curve segments for which the length exists. Okay, so I'm not going to deal with the non-rectifiable curves actually. Okay, curves with a finite length. So what would be this? How can I compute?
is rectifiable near.
One rectifiable.
सर इसके लिए जो पैरामीटर एग्जिस्ट करेगा सर वो शायद वो इंक्रीजिंग नहीं होगा.
So I'm saying I have this. Okay, my f is 1. And what is the meaning of a function being equal to 1 actually?
Constant function.
So it's a constant function. In other words, no matter what point you evaluate it, you're going to get 1. Okay? The question is, what would be this? So this is going to be 1. This f of p of t is going to be 1 multiplied by p prime of t dt and integrated. Okay? So this would be your s of c, arc length. So when you are integrating, so computing arc length is like integrating one scalar field, okay, that curve scale. ठीक है? नहीं ये बात समझ ठीक है? देखा ना? So whenever you have to, for example, solve a problem, compare this with the standard notion actually. So I'm saying that previously we said that okay, you have a 1 here, and I'm saying 1 is a scalar, it's not a vector, it's not like a vector of 1, 1, 1. This is just a number. So that means that you want to integrate a scalar field, okay, over the entire curve C. The question is, I'm saying that now my f is 1. In other words, no matter what point you take on the curve, you are associating a single number 1 to it. So when you are computing the integral of any scalar field, what you need to do? Take that scalar field, in other words, f of b of d, and multiply it with the magnitude of the b prime of d. So you get s of c. Okay? Second. Imagine you are interested in computing. So f is representing, for example, the temperature of the entire, curvature. Okay, so in other words, to each point, so you have a temperature field on a curve. Okay, to each point you have a different temperature. I would like to compute, say, average temperature for entire curvature. What should be its definition?
सर स्केलर फील्ड को इंटीग्रेट करेंगे सर.
Okay, so scalar field को integrate करेंगे for sure. Okay, so this is something that you have computed the entire temperature over. Okay, the cumulative temperature over the entire curve. Now I want to average actually. So what should I do? Over b minus a. But I know that I'm not talking about an interval. I'm talking about a curve actually.
सर उसके लेंथ के साथ
Exactly. So divide by the length actually. So divide by the length of the curve. Okay. So this would be. So what should I call it? So imagine. So you will have some exercises where you have to calculate the average value of the scalar field over the entire curve, and then you have to. So that's this is the average. Okay. ठीक है जी. Let's talk about some more properties of vector field. Okay. What are some properties of vector field? Integrating vector field over the curve. So what essentially we have done, okay, so we have essentially created two ways of integrating the scalar fields and vector fields to the onto the curve actually. So it's a new species of integrals, but you have to keep one thing. You always define new things in the terms of the old things actually in a theory. Okay. It's not always hard and fast rules. Sometimes you can define things from the scratch, but mostly if you are trying to define a new form of any integration, you will learn lots and lots of kinds of integrals actually. You will see that every such integral is basically broken down to the Riemann integral, some kind of a Riemann integral actually. Okay? That's what we like to make sense of it. So here's a little proposition. Just proving, just giving you, a way. So imagine f is a continuous vector field. F is continuous vector field. Okay. On a rectifiable C, rectifiable oriented C. So it has a particular oriented C. Okay. Then the integral of f onto the curve C is same as onto the reverse of a curve is same as that you compute the integral of f onto the curve C and negate it. And negate it. By the way, can you see, here's an interesting point. Can you see that the line integral of vector field is generalizing the line integral of vector field. Why?